This lecture is about simply typed lambda calculus. So previously, we learned this untyped lambda calculus. It's called untyped because in the syntax for lambda abstractions, there is no type. So this language has no element of types. Now we are going to study a variant of this untyped lambda calculus called simply typed lambda calculus. So we can think of this simply typed lambda calculus as a variant of untyped lambda calculus extended with types. So for example, in the case of untyped lambda calculus, we encode all these base types such as bool, net, and so on using lambda abstractions. So all these base types are encoded using lambda abstractions. In contrast, in the case of a simply typed lambda calculus, we can introduce base types such as, for example, bool, int, float, and so on using primitive constructs. So for example, we may choose to support the base type bool with the primitive construct true, false, and if then else. So unlike in untyped lambda calculus, where these Boolean values are encoded or simulated, in simply typed lambda calculus, we introduce base types and provide corresponding primitive construct. So that's the key difference. Now let's talk about how to design this simply typed lambda calculus. This is also a programming language, so it will have abstract syntax and it will have semantics. And in our case, we will be using operational semantics. In operational semantics, we introduce types in this language. So later, we will see that the lambda abstraction now has this form, lambda x a dot e. So in the case of untyped lambda calculus, we don't annotate this variable x, but here we are going to annotate this variable x with its concrete type. So now in this language, we have a new element called types, but types play no role in operator semantics. So in comparison with this untyped lambda calculus, the operator semantics is almost the same, and the changes are just nominal because these types play no role at all in reductions. So this operator semantics is quite easy to develop. And the major change here is we are going to introduce a new system called type system. So this is the new addition. In the case of untyped lambda calculus, we have only operator semantics and abstract syntax. But in the case of a simply typed lambda calculus, we have a new system called type system. So this is a major addition. So this type system enables us to assign types to expressions. So for example, given an expression E, we can answer the question, what is the best type that we can assign to this expression? For example, the best type that we can assign to this expression is bool, or it might be a function type, something like a bool, arrow, bool. So we will see the notation shortly. So the goal is we'd like to assign types to these expressions. So we will introduce a new judgment, of course, because this is a system, new system. So we introduce a new judgment, which is called typing judgment. And this judgment makes no sense unless we provide corresponding inference rules. So we introduce new inference rules called typing rules. So we will develop this typing judgment, and we will also develop these typing rules to formulate this type system. Then why do we need types? Type is very useful because it allows us to determine the form of the value that you can obtain from a given expression. So for instance, suppose that you are given an expression E, and this type system decides that it has a type bool. Then we have a good reason that we have a good reason to believe that this expression E eventually evaluates to either Boolean true or Boolean false. Not something completely unrelated, for example, integer 3. If this expression E of type bool eventually produces integer 3, then we'll be very surprised. So this type system calculates the type that can be assigned to a given expression, and with this type, we can anticipate the form of the value that this expression will produce. If this expression has a type, for example, int, then probably this expression will produce a value like 3 or 4 or something like this, but not something completely unrelated, for example, true or false. So this is the motivation for developing type system. We would like to be able to assign types to expressions before we run this program. And later, we will further investigate this nice property of types with type safety. So with this type system, now we can test if we can assign a type to given expression. That is, suppose that we are given a program or an expression E, and we ask the type system to type check this expression or determine the type of this expression. Then the type system might answer, okay, this expression E can be assigned the type bool. Or the response might be, no, this expression is bad. You cannot assign any interesting type to this expression. So the type system can answer like this one or this one. So in this case, we say that this expression is not well-formed, it's ill-formed. In other words, it is bad expression. And perhaps this expression, for this expression, it doesn't make sense to even try to evaluate this expression because this is ill-formed. It does not make sense. So in that case, the type system or the compiler will complain about your program being ill-formed. So we rejected this expression. But now what happens if this expression is well-formed? In this case, this is well-formed. The type system decides that your expression is well-formed, so we can assign a valid type, such as a bool, to this expression. And then this type safety property comes into play. With this type safety, the type system guarantees that this well-typed expression, this well-formed expression. Okay, this is a nice expression. This is a bad expression. This nice expression does not go wrong at runtime. Something really bad does not occur when you are computing this expression. That's the power of this type system with this type safety property. Notice that not every programming language provides this type safety. For example, suppose that you have program written in the C language. Okay, we have this C program. You try to compile this program, and the compiler says, okay, this program is okay. So you execute this program, but later something bad can happen. So for example, null pointer dereferencing or trying to add Boolean values, a Boolean value with another Boolean value or something like this. So something bad can happen despite the fact that the compiler says this program is okay. And that's because this C programming language does not have this type safety. It does not have this type safety. So even if this program is well formed, at runtime you might encounter some stupid bugs. That's not the case for this language with type safety. This type safety guarantees that if your program is well formed or well typed, then it does not go wrong at runtime. So we will come back to this property type safety later. So for now, remember that the motivation for developing this type system is we'd like to be able to assign types to expressions so that we can tell what kind of values to expect by evaluating these expressions. Mild introduction to type system. Now let's develop uh, this new programming language called simply typed lambda calculus. So we will need abstract syntax, operational semantics, and finally, type system. So let's first talk about this abstract syntax. So needless to say, we need a new syntactic category for types because it's a simply typed language. So we introduce new syntactic category called type. So we use meta variables A, B, C, and so on for types. So types are defined as either P, base type, or this function type. So this base type, so P denotes this base type. So we may choose to introduce any base type that we like. So for example, we could introduce base type bool for Boolean values, or we could introduce base type like int for integers, or we could introduce another base type float for floating point numbers, and so on. So you may choose any base type you like, provided that you later provide this language construct. So for our lecture, we will just simplify the whole presentation by assuming this single base type bool for Boolean values. And this is the function type. So we have this a arrow a, and if you have something like a1 arrow a2, it's basically types for functions from a1 to a2, which means that it takes arguments of a type a1 and returns values of type a2. So the result type is a2, whereas the argument type is a1. So for instance, if you have a bool, arrow bool, it takes a Boolean value as an argument and returns another Boolean value as the result. So that's the function type. So for our lecture, we don't use these base types. And just like OCaml programming, this arrow symbol is right associative. So for example, A arrow, B, L arrow, B arrow, C. So this B has arrows on both sides, but this arrow symbol is right associative. So this one prefers to associate with whatever lies on the right side. So you can imagine that these parentheses are omitted. So it's right associative. So remember that you can always add new base types. In that sense, this language is extensible. Later, if there is a need for integers, we can introduce new base type, something like this. So, but for this lecture, we will use this base type bool only. Next, we need to define these syntactic category expressions. And expressions, we inherited the three constructs from untyped lambda calculus: variables, lambda abstractions, and applications. But the big difference here is that because we are talking about types, this time we annotate this bounded variable x with its type. So in other words, we explicitly specify the type of this bounded variable with this type A. So it says that this lambda abstraction, its formal argument is x, and its argument type is A. That's what this annotation says. So we inherit the three language constructs from untyped lambda calculus, except that for this lambda abstraction, now we want to annotate every bounded variable explicitly with its type. Next, we want to provide the primitive construct for this base type. So in our case, we consider only a single base type bool. So you have to provide something for bool here because you are designing this programming language. So as a designer for this programming language, you decided to support the base type bool. So you are supposed to provide some language construct, primitive construct for bool here. So it's your decision. So in our presentation, we will use the familiar forms. For Boolean values, we introduce a Boolean constant true and Boolean constant false, and the familiar form conditional expression: if expression E, then another expression E, else yet another expression E. And finally, we have to define the syntactic category values. So first, just like untyped lambda calculus, this lambda abstraction is counted as a value. So we have lambda x a dot e as a value. And next, we have to choose values from this primitive construct for Boolean construct, Boolean type. So true is definitely a value, and false is also a value. And probably this is not a value because there's room for reduction. So this if then else conditional expression is not counted as value. So for our example, for our case, we decided to introduce a single base type bool, and for this base type bool, we introduce these three language constructs, and two of them are values. And of course, like I said before, we may decide to introduce new base type, for example, int, in which case you have to provide primitive construct for integers, and you also have to extend the set of values as well. But for our case, we only consider this base type bool only. So that's the abstract syntax. Now let's talk about operation semantics. So remember that the operation semantics for this simply typed lambda calculus is almost the same as the one for untyped lambda calculus, except that we have to provide rules for this base type bool. And also, this type does not interfere with this reduction at all. So the change in operation semantics will be very simple and almost nominal. So let's develop the operation semantics for this language. So for operation semantics, just like the operation semantics for untyped lambda calculus, we will have to define, for example, this free variable function, and we also have to define this capture avoiding substitution, return e for e prime for x in e. And finally, we will have to define this reduction judgment and also reduction rules. But remember that there's nothing inherently new here, perhaps except for the reduction rules for this if then else construct, because this is a new component. For these existing three components, variables, lambda abstractions, and lambda applications, the operation semantics is almost the same, except that you have to do something about this type annotation. But this type does not play any role at all in reduction, so you can simply ignore these types in any part of these definitions. So for example, let's define this free variable function, the free variable. So the definition is almost the same, except that in this case, previously in untyped lambda calculus, the definition was free variable expression e minus variable x. And even if we introduce this type annotation in simply typed lambda calculus, this equation does not change because this one has nothing to do with this type annotation, has nothing to do with free variables. It does not change, it does not affect the status of this variable. This variable stays as a bounded variable whether you have this type annotation or not. So there's no change here. And similarly, there's no change in the definition of this one. But unfortunately, we have three new language constructs here. So we have to extend this function. But it's trivial to define. So the set of free variables in this expression is empty because there is no variable here. And similarly, free variable false is also empty set. And what about free variable if e then e1 else e2? It could be that this expression e and this expression e1, this expression e2 might harbor some variables. So we have to make recursive calls. And the answer is free variables e union free variable e1 union free variable e2. So although we need three new cases, the definition is almost straightforward. Next, we have to define this capture avoiding substitutions. Again, the definition is almost the same as before, in untyped lambda calculus, except that we have to provide the three new cases for true, false, and this if then else conditional expression. And for this lambda abstraction, again, the definition is almost the same because you can simply ignore this type annotation. The types do not interfere with the reductions. So let's simply state that E prime for x in E is almost the same as in untyped lambda calculus, except that we have three new cases. E prime for x in true, in this case it's true because you cannot find any variable inside the true. And similarly, E prime x for false is false. And finally, E prime for x if E then E1 else E2. And there are no variables here, so you can simply propagate the substitution into these three individual expressions. So the answer is if E prime x E, then E prime x for E1, else E prime x for E2. So in this way, we can define these capture avoiding substitutions. Finally, let's introduce this reduction judgment. And the meaning of this reduction judgment is the same as before. So it says expression E reduces to expression E prime. And we have to provide the corresponding reduction rules. And similarly to the first two cases, the reduction rules are almost the same as in untyped lambda calculus for its variables, lambda abstractions, and applications, except that we have to annotate every this variable binding with a type is a type, but we can simply ignore this type when we are reducing expressions. So it's straightforward to extend the previous reduction rules for simply typed lambda calculus. So for example, let's quickly write the reduction rules based on uh, reduction rules based on call by value, for example. So we have this, the first rule, if E1 reduces to E1 prime, then the whole expression reduces to E1 prime E2. And if everything goes okay, you'd have lambda abstraction. But notice that here we have now this type annotation, unlike in untyped lambda calculus. But it doesn't matter because this type annotation does not interfere with the reduction. And if this argument E2 reduces to E2 prime, then we want to reduce the whole expression again. And finally, if we have lambda abstraction applied to value v, we perform beta reduction. So you have value v for x in E. So these three reduction rules are essentially the same as in untyped lambda calculus, untyped lambda calculus with a call by value, except that you have to make a small adjustment to the syntax because now every variable in this lambda abstraction must be annotated with their types. So that's the only difference. So we simply annotated this one here, here. Then we obtain the reduction rules for simply typed lambda calculus based on call by value. And there are three remaining cases because we introduced this language construct. So similarly to this free variable function and capture avoiding substitutions, we have to introduce reduction rules for these three new language constructs. So that's the only remaining job. We can simply inherit all these reduction rules from untyped lambda calculus with a minor adjustment, like this one, and this one. Now, let's think about the reduction rules for the three forms of expression, the true, false, and conditional expression, if E then E1, else E2. First, there's nothing we can do about this true and false because they are counted as values. So there are no reduction rules for true and false. And what about this one? Imagine that you are designing this programming language. So there is no definitive answer to this question. You may choose your own style of operation semantics. But perhaps everybody will try to reduce this conditional expression E first, because that's what we would like to see first before looking at this then expression and else expression. So a reasonable choice here is if you have expression if E then E1 else E2, you'd like to try to evaluate, reduce this expression E first instead of E1 and E2. So suppose that expression E reduced to expression E prime, then you'd like it to reduce the whole expression into E prime, then E1, else E2. And you can assign some interesting name to this reduction rule. So this is a reasonable choice. And if everything goes okay, probably this expression E eventually will produce either true or false. Of course, this may produce some unrelated value like lambda abstraction. But in that case, later we will see that such a bad expression will be rejected by the type system. So if everything goes okay, you will produce either true or false from this expression E. So suppose that you have now if true, then E1, else E2. Again, here it's your choice how to decide how to reduce this expression. So this is if a true case. But a reasonable choice here again is just to follow our intuition. Because this is true, we simply choose this expression. So the whole expression now reduced to expression E1. So that's a reasonable choice. And there's a symmetry case. If this is false, then we ignore this expression E1 and instead decided to take the else expression. So this is E2. So this is if false. So these are three reduction rules that we choose. Note that there is no definitive answer to the question of what are the right reduction rules for these if then else expression. There's no such an answer. It's your choice. And in our case, we choose to use these three reduction rules because these three reduction rules just seem okay. They seem perfectly reasonable. But of course, you may choose some different strategy. So for instance, although we are not going to discuss this reduction rule, in this case, if expression E1 reduces to E1 prime, you might actually choose to keep everything here. But this rule is fine, this reduction rule is fine, although it does not really comply with the intuition of reducing this expression. So we will not use this funny reduction rule. We will just use the simplest form, which is to return expression E1. So these are the reduction rules. So we extend, basically what we did is we inherited the three reduction rules from untyped lambda calculus with a minor adjustment with these type annotations. And for these three new language constructs for this base type bool, we choose these reduction rules. And this completes the formulation of operation semantics because we extended this function, pre-variable function, and also we extended this capture avoiding substitution, and finally we formulated this reduction rule, the reduction judgment and reduction rules. So this is the operation semantics for the simply typed lambda calculus. So as you have noticed already, you have to carry these types all along because now types are part of the syntax. But these types play no role. It does not play any interesting role in the reduction judgment. So for that reason, this operation semantics is almost the same as the one for untyped lambda calculus with these nominal changes and new reduction rules for these base type bool. Now let's go back to here. So we are in the middle of designing this new language called the simply typed lambda calculus, and we gave a new abstract syntax, and we finished this operation semantics. Now it's time to discuss the last component, the last new component called type system. So let's develop this type system. So the goal of developing this type system is, given an expression E, we'd like to, given this expression E, we'd like to calculate the best, we'd like to calculate its best type. So this is informal description of what this type system is for. Given an expression E, we'd like to find out its best type, informally speaking. And this type is very useful for analyzing this expression. So for instance, if an expression E has a type bool, there is a good chance that this expression eventually produces either true or false, not some lambda abstraction. This is unlikely unless the programming language is ill-designed. The purpose of developing this type system, and this is a new system with a new typing judgment, and this new form of judgment, so we have to provide the inference rules, and the inference rules are called typing rules. Here's an example. Let's consider lambda x a dot x. So given this expression, we'd like to find out its best type, although the notion of being best is ambiguous at the moment. So informally speaking, we'd like to find out the best type that we can assign to this expression. Then, how do we calculate the type? So first of all, it is lambda abstraction, so it's going to have this function type. And we already know the argument type because we explicitly annotate this variable x with its type. So the argument has a type A. So we already know this left side of this arrow. And the remaining question is, what is the right side here? That is, what is the type of this body? If this body produces some type B, then we would write B here. So now the question is, what is the type of this body? Let's suppose that at the moment we don't know what the body looks like. So its type is unknown at the moment. Now let's try to find out the type of this body, the body expression. And inside this body expression, we might have many instances of this variable x. So for instance, we might have something like lambda x a x. The simplest example, in the expression for body, the body expression here, we have an instance of variable x. So in general, this body expression might contain lots of variable x. So therefore, in order to determine the best type for this body, we have to assume that x has a type A. In other words, in the middle of calculating the type of this body expression, we have to assume that x is a type A. Now let's go back to the concrete example. Suppose that this was simply x. Now we assume that x is a type A, and now we'd like to find out this expression. And this expression is x. So according to the assumption here, it has a type A. So the body has a type A. So as a result, this is the best type, A arrow A. This is the best type that we can assign to this expression. So there's no surprise here. This lambda abstraction is going to have this A arrow A. But the point here is that when calculating the type for the body expression, or when we are type checking the body expression, we have to remember the assumption that x is a type A. So we have to carry this assumption all along when we are type checking the body expression. So this observation leads us to introduce new concept called typing context. It literally says a typing context is a context in which typing occurs. So when we are type checking this body expression, the context is the context contains the assumption that this variable x is a type A. So informally, this typing context is going to be just a collection of assumptions of this form. So that's the intended meaning of this typing context. So let's formally define this typing context. For historical reason, we usually use these Greek letters gamma for typing context. So typing context gamma is defined as either empty set. So this is our notation for empty set, or an existing typing context extended with new assumption that x has a type A. So the meaning of this notation is assumption that x has type A. And we call it this guy as type binding. Type. So typing context is essentially a collection of type bindings of this form, of the form x colon A. And the interpretation of x colon A is variable x has a type A. And typing context is just a bunch of assumptions of this form. And this is our notation for the gamma union x colon A, because we don't want to use this mathematical notation, which is quite cumbersome. And furthermore, we'd like to abuse this notation. So for instance, instead of writing gamma union gamma prime, this is fine, but we'd like to simply write gamma comma gamma prime. So this is our simplify the notation for writing this union. So these two guys are actually the same. Or we could write gamma x colon A gamma prime to mean that gamma union x colon A union gamma prime. So according to this definition here, gamma is basically a collection of type bindings. So to be precise, let me get rid of this. So remember that we decide to it's okay to abuse this notation because there's no ambiguity arising in this notation. So remember that this typing context gamma is a collection of type bindings. So to be more specific, it is unordered set of type bindings of this form. So usually gamma can be rewritten as x1 has type A1, x2 has a type A2, and so on, and xn has a type AN. Of course, it may contain no type binding if it is an empty set. And there's one question here. What if these variables clash in their names? What if we contain two type bindings that clash with each other? So this is B, where A is not equal to B. So to simplify the whole presentation, we assume that all these variables are distinct. And so these variables are all distinct. That's the assumption that we make when we deal with the typing context. And as we will see later, we can always rename bounded variables. Actually, we have seen this phenomenon, alpha conversion, before. So for example, so these variables all come from this lambda abstraction. And if this particular variable x induces some problem, like name clashes, then we can always choose to rename this one to something completely new, some fresh variable. So we can rename this one to the z. So in this way, we can aggressively apply alpha conversion, or we can aggressively rename these bounded variables so that all these variables in any typing context are all distinct. So that's the assumption that we make. So now we defined this typing context, and it's a time to introduce typing judgment and typing rules. So let's first talk about typing judgment. So typing judgment takes this form: gamma turnstile expression A. This symbol looks like a turnstile. That looks like this one, and this revolves around. So this is the typing judgment that we will be using. Typing judgment, and it says, let's say gamma is x1 a1, x2 a2, blah blah blah, xn an. Then this typing judgment means that under the assumptions provided by typing context gamma, that is, we assume x1 has a type a1, x2 has a type a2, and so on, xn has a type an. Then under this typing context gamma, expression E as type A. So that's the meaning of this typing judgment. So in the course of type checking this expression E, in other words, when we are trying to find out the type of this expression E, which is A, We may use the assumptions in typing context because these are all assumptions. Typing context gamma is a collection of type bindings of this form, and each type binding is just an assumption. X1 has a type A1 and so on. So you may choose the assumption, any assumption in typing context when we type check this expression E. So this is a typing judgment. Now we have introduced typing judgment, and let's develop typing rules. So remember that this typing judgment means under typing context gamma, expression E has a type A. So this is typing judgment. And let's talk about typing rules. First, we have expressions are variables, lambda abstractions, and application, and true, false, and this conditional expression. So for each of these components in the syntactic category expression, we will need a typing rule. So let's first talk about this variable. Under typing context, the gamma expression variable x has a type something. Then the question is, how do we determine the type of this variable? Well, you cannot decide the type of this variable without looking up this typing context, because no further information about this variable x is given. So you have to go back to this typing context and see if there is a type binding of this form. If you find the type binding of this form, it means that x is assumed to have type A. Therefore, you decided that x is type A, simply because this type binding says x has a type A. It's an assumption that you may use as many times as you like. So therefore, this is the typing rule for variable. If you find this type binding in typing context gamma, it says that we decided to assume x is a type A. So x is a type A, so therefore x is a type A. So this rule is called the bar rule. You may rephrase this rule, rewrite this rule in this form if you don't like this premise. If this type binding is found inside this typing context, then x has a type A. So the presentation is slightly different, but their meanings are the same. If you have this type binding of this form inside the typing context, you may decide x is a type A. So we have finished the typing rule for this variable. Next, let's talk about typing rule for this lambda abstraction. Again, on the typing context gamma, we'd like to find out the type of this lambda abstraction. So we already have half of the answer. It's going to be something like A arrow some stuff, because it is a lambda abstraction, so it has this function type as indicated by this arrow, and we already know the answer, the argument type, which is A, so A goes here. So the remaining question is, what is the return type? So we have to figure out the type for this body expression. But remember that inside this body expression E, you might have lots of references to this variable x. So this is not enough, because inside expression E, you might have a variable x. So therefore, you have to augment the typing context with new assumption x is type A, which means that while you are trying to type check the expression E, you might have to use this assumption that x is a type A. So without this assumption, you may not be able to actually find out the type of this expression E. So with this new typing context, you try to decide the type of this expression E. Let's just say the answer is B. Then the body has type B, so the return value has type B. So this is the typing rule for lambda abstraction. And this rule is called arrow introduction rule. Because if you read this rule top down, you end up introducing. If you read this rule top down, you end up introducing this arrow symbol. So this rule is usually called arrow introduction rule. And also remember that in this typing context, it's safe to assume that all these variables are distinct. Because if something bad happens and the variable x is already found inside, if type binding of this form is already found inside the gamma, you may always rename this bound variable with the alpha conversion. So it's safe to say that all variables inside this typing context are different. So in other words, you can simply assume that this variable x is completely fresh. So this case is gone. Now let's talk about this expression. The question is, under typing context gamma, how can we decide the type of this expression E1, E2? First, we have to type check these two individual expressions. So let's find out the type of expression E1, and let's find out the type of expression E2. If this expression has a valid type at all, first we observe that this expression E1 must have some function type. Otherwise, this expression doesn't make sense. So for instance, if this expression E1 had a type bool, then this is just a nonsensical expression because you cannot apply a Boolean value to its argument. So first, we have to make sure that this expression E1 has a type something arrow something. Because we don't know what they are, let's just say they are A arrow B. So this judgment says that expression E1 has valid type A arrow B. Now let's talk about expression E2. In order for the whole expression to have an interesting type, both these individual expressions E1, both E1 and E2 must have valid type. And if we think about the meaning of this lambda application, this E2 must have the same type as the argument type here. Otherwise, we don't expect the expression E1 applied to E2 to have some interesting type. So for instance, let's just say this expression E1 has a type bool arrow something. Then E2 must have also type bool. Otherwise, you will not be able to apply expression E1 to E2 because the argument type does not match the type of the argument, the actual argument. So we require that this expression E2 have the same type as discovered here. So that's the second part of the premise. And we usually write this rule, we usually call this rule introduction elimination rule. Because if you read this rule top down, you end up eliminating, this E stands for eliminate. If you read this rule top down, you end up eliminating this arrow. So in the premise, you have this arrow. Now, arrow has been eliminated. So in that sense, when we read this rule top down, arrow is eliminated. So this rule is called error elimination rule, which is dual to the previous rule, error introduction rule.